we'll talk now about how to compose functions. So to reiterate, this is an operation that applies for functions that did not apply for just plain old numbers or variables. So let's look at the definition before we apply it to several examples. So we say that for two functions, f and g, their composition of f with g is a new function denoted with this circle here, and it is given by the following rule. F composed with g is equal to first applying the function g and then applying the function f. So I'll say first apply g, then apply f. We can, of course, similarly define g composed with f as first apply f, then apply g. So let's look at a quick example. If I have f of x is equal to x plus 1 and g of x is equal to x squared, then I claim that f composed with g is equal to x squared plus 1. And we see this by noting that f composed with g of x is equal to f of g of x. So first I replace g of x with its rule, x squared. And then I plug this into the formula for f. So to compute compositions of functions, I just first do one function, then the other one. It is important to note, though, that the order matters. If I compute f and then g, this is not the same as doing g and then f. Another way of saying this is that unlike addition and multiplication, where order does not matter, composition of functions is not commutative. It's more like subtraction and division in this way, where the order does matter. So I'll highlight that here. Composition is not commutative. If I do f and then g, like I do here, that's not the same as doing g and then f. And we can see this in our particular example. I saw that f composed with g was x squared plus 1. But if I do a similar calculation, I see that g composed with f is actually x squared plus 2x plus 1. So there's something different here. This is almost always the case with composition, that if you do one and then the other, it's different than if you did the second then the first. So you have to be very careful with what's being asked for. Let's look at just a couple examples where I will have two functions. I'll compute their sum, some difference, multiplication, division, and then also these compositions. And we'll see exactly how this works. So here's a first example. We'll take f of x to be equal to x squared and g of x to be equal to 1 minus x squared. So we'll start by finding their sum. So f plus g of x, this is just equal to f of x plus g of x. So x squared plus 1 minus x squared, which is equal to 1. So their sum is just the function 1. Let's look at f minus g of x. This is equal to, as seems natural, f of x minus g of x. So x squared minus 1 minus x squared. And this gives me 2x squared minus 1. Let's look at f times g of x. So this is f of x times g of x. So x squared times 1 minus x squared. And you could expand this, if you like, to x squared minus x to the fourth. Just for fun, let's also do a division. F divided by g of x. So f of x divided by g of x. So x squared divided by 1 minus x squared. So this is fine, but note f divided by g is not defined at plus and minus 1, because this would give division by 0. Let's look now at the compositions. How about f composed with g of x? Well, so we compute this by the formula as f of g of x. So this is equal to f of 1 minus x squared, because that was the rule for g of x. X goes to 1 minus x squared. Now the rule for f of x was x goes to x squared. So I take this and square it. And if you like, you can expand it out and get 1 minus 2x squared plus x to the 4th. And just for good measure, let's do g composed with f. So this is g of x squared, which is 1 minus x squared squared, so 1 minus x to the 4th. And we'll remark again that f composed with g does not equal g composed with f here, because 1 minus 2x squared plus x to the 4th is different than 1 minus x to the 4th. Let's look at another example. We'll make these with rational functions. 1 minus x. And let's make g of x 2 over x plus 1. So we'll play the same game. We'll do some additions and then some multiplications and compositions to see how this works. So first, let's do f plus g of x. So I have 1 over x minus 3 plus 2 over x plus 1. So how do I add fractions? Even if there's variables in the fractions, I find the common denominator. So we'll do that here. This is equal to x plus 1 divided by x plus 1 times x minus 3 plus 2 times x minus 3 divided by x plus 1 times x minus 3. My common denominator was, or is, this thing here. And now I am permitted to add in the top, so I get x plus 1 plus 2x minus 6. Same denominator, and I'll just put everything together. 3x minus 5 divided by x plus 1 times x minus 3. So it's simple to add two functions as long as I know how to add fractions, for example. So the rules that applied for numbers also apply here. Let's just look at a product example. F times g of x. This is 1 over x minus 3 times 2 over x plus 1. Now, multiplying fractions is easier than adding fractions generally. I just multiply the denominators and multiply the numerators. So I get 2 divided by x minus 3 times x plus 1. Okay, so fairly straightforward, I think. And let's have some fun here. Let's look at the compositions. F composed with g of x, with this open circle to denote composition. This is equal to f of, well, what's the rule for g of x? X goes to 2 over x plus 1. So I get this, and now I plug in that into the formula for f. So 1 divided by 2 over x plus 1 minus 3. Kind of ugly looking. There's a fraction inside of a fraction. So what I'll do is I'll simplify this. I'll write this as, I'll multiply top and bottom by x plus 1, and I will get x plus 1 divided by 2 minus 3 times x plus 1. And again, this was done by multiplying top and bottom by x plus 1. So I get x plus 1 divided by negative 3x minus 1. Okay, and we'll do G composed with F also. I remember the rule for F, it's x goes to 1 over x minus 3. So this gives me this, and I will simplify this by doing x minus 3 here to get 2 times x minus 3, 1 plus x minus 3, which yields ultimately 2x minus 6 divided by x minus 2. So again, I see that if I compose f with g and g with f, I don't get the same thing. This is in general true for compositions and is an important thing to remember. This is like a nice true-false question they could ask you on the CLEP. Is it true that compositions commute? That f and g is the same as g and f? The answer is no. So it's more like subtraction and division than it is like addition and multiplication.